today. So the last speaker is the Hee-Cheol Kim from Postex. She will tell us about the finite landscape of the supergravity.
Okay, yeah, first of all, I'd like to thank the organizers, particularly Sarah and Sergio, for putting together this wonderful workshop and also for the invitation. So today I'll be talking about the finite landscape of the 1-0 supergravity, and this talk is based on my paper last year with Kumnun Bafar and Kai-Su at Harvard University. I realized that I'm the only one who is talking about gravity in this workshop, so I'm a bit worried, but at least I have some. Okay, yeah, I have something to talk about keywords and symmetries and associates. So yeah. Okay, let me begin with the motivation. So in string theory, the number of known vacuum, in particular in Minkowski space, is finite. And in mathematics, there is a related conjecture by Yau. He proposed that the number of Calabi-Yau manifolds in every dimension may be finite. So here he's counting only the topologically distinct manifolds, and he's just saying that maybe such number, so number of such manifold is finite. So this is, of course, not proven, and it's still an open problem, but mathematicians made significant progress for this conjecture. They actually proved that number of elliptic Calabi-Yau manifold. So if we have an elliptic vibration structure for the Calabi-Yau manifold, then that number is finite for any dimensions. So this math proof and also Yau's conjecture, together with all the known string theory examples, suggest that string compactification may provide only finite number of consistent quantum gravity theories. So in particular, this math proof tells us that the number of shifted supergravity theories engineered in F theory compactification is finite. So this is quite surprising. So this idea led to some conjectures in swamp-land program. So first, finiteness conjecture proposed by Bapper, Douglas, and Acharya and Douglas. And they claim that the set of consistent quantum gravity vector with fixed cutoff is finite. And also number of massless field has an upper bound. And there is also a related swamp-land conjecture called the string lamppost principle, or often called the string universality, which are recently studied in many papers. And it claimed that all consistent quantum gravity theories arise from string theory. So if this conjecture is true, then it means quantum gravity landscape precisely agrees with the string landscape. As we know, these are bold conjectures, and we don't know how to prove it at this moment. But at least for the theories with a large amount of supersymmetry, we can test these conjectures in very, very concrete manner. For example, for the theories with the 32 supercharges, and actually we can use consistency of this theory, low energy theory together with the supersymmetry to fully determine the low energy theories. And it turns out that all the low energy theories preserving 32 supercharges are realized as toroidal compactifications of M theory. So therefore, the number of such a theory with 32 supercharges in any dimension is finite. And also they are all realized in string theory or M theory. So these two conjectures are rather trivially satisfied for the theories with the 32 supercharges. But if we reduce the number of supercharges, this conjecture becomes much more complicated. But there are, sorry? Oh, no. So here, this review is for generic dimensions. So later I focus on shifting. Yeah. Okay, but the theories with the shifting supercharges, there are many recent progress. So with the shifting supercharges, massless metal content consists of not only gravity multiplet, but now we have vector multiplet. So the low energy theory is characterized by the gauge group tree. And there is, surprisingly, a bottom-up argument saying that the rank of such gauge algebra or gauge group is bounded by 26 minus d or the given dimension d. And this bound precisely agrees with the bound known in string theory. And we can prove this bound using the proof string argument together with some sample-end conjectures, which was done in this paper. So finiteness conjecture hold in in any dimensions with 16 supercharges. This is quite surprising. So for example, Cheung and also Antoine discussed about n equal 4 super-Yang-Mills in 4 dimensions. And there is no constraint on the rank of gauge algebra. For arbitrary large gauge algebra, we have very, very nice 4-dimension n equal 4 super-Yang-Mills. But this claims that if the rank is greater than 22, then that theory is no longer Prince. Okay, so yeah, we have very bad behavior of such a theory when we couple to gravity. Without gravity, they are all consistent. But with gravity, when the rank violate this bound, they are inconsistent. So this finiteness conjecture provides very, very sharp distinction between ordinary field theories we usually talk and the gravitational theories. And furthermore, you can use this bound to argue that string Lampos principle hold in 10 dimensions with the 16 supercharges. So in 10D, we have chiral theories. So we have gauge and gravitation anomalies. And such anomalies can be cancelled if gauge algebras are the following. So we have 4 allowed gauge algebras. As we know, E8 times E8 and SO32, these 2 gauge algebras are realized in string theory. On the other hand, the other 2 gauge algebras, including abelian factors, has no realization in string theory. Okay, so it was an open question whether string Lampos principle hold in 10D with 16 supercharges. But if you look at these gauge algebras, the rank of these gauge algebra is far beyond this rank bound we found. Okay, so it means the theory with these large rank gauge algebras are actually inconsistent, and they belong to the swampland. Actually, you can prove this one using, again, proof string argument, basically. So string Lampos principle hold in 10D with 16 supercharges. But it's not easy to generalize this idea directly to, oh, yeah.
Maybe this just increment of the swampland. What about the large N and holography?
So large N holography exists in the ADS background, right? So gravitational theories are in ADS background. So here we are focusing on the Minkowski space. But in ADS background, you can argue another finiteness conjecture with fixed cutoff. Okay, so of course, if you increase cutoff to infinity, then you can have a large answer. But here we are focusing on Minkowski space. So ADS is another question to ask. Yeah, good question.
This bound come from anomaly or no?
Very good. So unitarity of the world CFT living on the string object. And so in all these 16 huge cases, we have string BPS strings. And if we require unitarity of the world CFT, then this bound follows from. Yeah. Essentially, it's whether we can realize the current algebra on the world CFT for the given central charge. So this bound is like, so if you want to realize current algebra on world sheet, it requires some additional degrees of freedom. And if the number of degrees of freedom cannot fit in with some finite central charge, it will violate the unitarity. So this condition is essentially coming from it. Yeah, good. Any other question? The problem is it's not easy to generalize this idea to lower dimensions, but at least in 9D and 8 dimensions with the 16 supercharges, there are many, many papers, recent papers, showing that string Lampos principle continues to hold.
6 dimension territory, your theory called Pokemon theory.
Yeah, very good question. But there are some, last year or the year before, there is a paper by Miguel Montero, and they argued that on the circle compactification and by imposing the no global symmetry and so no global symmetry conjecture, and you can exclude such theories. But yeah, so quantum is inconsistent. But you have to assume kind of some sample and conjecture like no global symmetry. Yeah, very good question. Okay, then the natural next question is, what about the series with field supersymmetry in less dimensions? So for this, today I'll be focusing on 61 zero supergravity series preserving 8 supercharges. And I'll provide very, very strong evidence supporting both finiteness conjecture and string lamppost principle. And as I explained, there is a math conjecture for the finiteness of the elliptic Calabi-Yau manifold. So this simply says that a number of 60 supergravity series coming from geometry or F series finite. So we already have some kind of finiteness structure, at least for some subset of this 60 supergravity series. But today I'll give you just using the field theory argument to show the number of massless field in any generic 60 series is actually finite. Okay. So more precisely, I'll give you a bottom-up argument using only field theory argument to show that number of massless field in 60 supergravity theory has an upper bound. And I will show you how to compute that bound exactly. And the series saturating this bound are realized in concrete string theory models. But this argument is based on the following two assumptions. So first assumption is there are BPS strings at every point on the boundary, at the boundary of tensor moduli space. So in 6 dimensions, as I will explain soon, we have the moduli space called the tensor moduli space, and it's defined with the boundary. And every point on the boundary, including, in particular, including the boundary at asymptotic infinity. So we have BPS strings. This is our assumption. But in all known string theories, such boundaries are defined by new light degrees of freedom there associated to the either 6S CFTs or little string theories or critical string in all known examples. And they all have tensionless BPS strings at the boundary. So I think this is a natural assumption. And second assumption is the classification of 6S CFTs and little string theories, which are studied extensively almost 10 years ago, including many people in the audience. And I'm claiming it's complete. So this is our second assumption. And this classification scheme discussed in these papers actually covers all the known construction method for 6S CFTs and little string theories, including the top-down approach, such as brain construction and geometry realization, and as well as bottom-up gauge theory descriptions. So I believe this is also a reasonable assumption. Okay, so these are two assumptions I will make, and then using the field theory argument, I'll show there is a finiteness structure in 61 zero supergravity. Any question? Is it clear? Okay, good. So this is my plan. So I'll start with a review on 61 zero supergravity. Then I'll explain some small key properties of tensor moduli space and BPS strings. Then I'll show you how to prove the finiteness of number of massless field in 61 zero supergravity. Then I'll compute the exact bound on the number of massless field and show you the bounds are saturated by F-theory models.
Of the classification of equal modules equal and there is one no problem.
What is what?
The potential with the 1,0 supergram.
So if we have, so I'll explain in detail more, but roughly, so we have supergravity, and supergravity contains some CFT or little string theory as a component. For example, many CFTs can be obtained by taking the gravity decoupling limit of some gravitational theories. Okay, so supergravity has some component inside, such as CFTs and little string theory. But I'll explain in more detail. So it's surprising. We have studied usually, in my career, actually, I studied only CFTs mostly. But now we can use our study, our knowledge about the CFT to argue some important properties of gravitational theories. Okay. So this is the idea. Okay, in 60, so let me briefly, very briefly, into this Hee-Cheol supergravity. In Hee-Cheol, there are 4 types of massless supermultiplets. Firstly, we have, of course, gravity multiplet, which contains graviton and self-dual two-form field B plus and gravitino. And there are many tensor multiplets, with each containing the anti-self-dual two-form field and a real scalar field, which I will call J. So J is a collection of the real scalar field in every tensor multiplet. Then the value of this scalar field parameterize tensor moduli space, which I explained. There are also vector and hypermultiplet, and I'll call the number of tensor vector and hypermultiplet as T, V, and H. And my claim is, quite surprisingly, these numbers are finite. Okay? It's very different from ordinary field theory. We know infinite families of consistent 61 zero SCFTs and also little string theories. But once we couple gravity, no, many of them are inconsistent. We have only finite number of massless fields. More precisely, I will show you that the number of tensor multiplet is bounded by 119.3. And furthermore, this bound is a sharp bound. It means you cannot improve further. Okay? We actually have concrete, consistent quantum gravity theory saturating this bound. So you cannot improve. Okay? And after our paper, there are 2 more papers discussing the number of, so bound on the number of tensors. You cannot see. So I will. Oh, not good. Okay, yeah. So 2 more papers discussing the bound on the number of tensors. Firstly, using the geometric analysis by Becker and Lee. And secondly, by Hamada and Lajes, they used the global anomalies and SCFT classifications to show the number of tensors is bounded in this way. So if you compare, then our bound is much stronger than their bound, and our bound is sharp bound. Okay, so they need some new idea to improve their method.
They also assume that something will.
No, for example, geometry case, my assumption is automatic. So you don't need to assume this one in geometry because it's already there. Because we believe geometric classification is done, and the boundary is always comes with some Morricone generators. So geometrically, these 2 assumptions are not assumption; it's proven. Yeah. Yeah. Second approach is a kind of SCFT classification they assumed. Yeah, kind of. Okay, Hee-Cheol theory, these theories are 1-0, chiral theories, so we can have gauge and gravitation anomalies. And in Hee-Cheol, we can cancel such anomalies using the Hee-Cheol Green-Schwarz mechanism if anomaly polynomial factorized in this way. So in Hee-Cheol, the anomaly polynomial is A form. So if it's given by product of 2 4 forms, then we can use a Green-Schwarz mechanism to cancel all the anomalies. Here, omega is a tensor intersection form with 1, T signature. Here, T is the number of tensor. And the coefficient here in front of R square and the field strength square are called anomaly vectors. But basically, the low energy effective field theories are specified by the structure of this intersection form and anomaly vectors together with the meta contents. Then this factorization condition provide very strong constraint on the massless spectrum. For example, gravitation anomaly cancellation condition imposes that the combination of number of hypermultiplet, vector, and number of tensors should satisfy this constraint. Okay, and we have more conditions from the factorization condition. However, it turns out that the conditions or constraints coming from anomaly cancellation are not enough, not strong enough to cut down the number of massless fields to finite. And in fact, there are many papers discovering new infinite families of anomaly-free supergravity theories. For example, this paper discovered an infinite family of anomaly-free theories with this number of tensor and this gauge algebras. Here for arbitrary k, actually all these theories have no apparent perturbative anomaly. Okay, so finiteness conjecture in Hee-Cheol is very, very non-trivial. because we have infinitely many looking consistent series at low energy. But today, I'll show you that most of these series are actually inconsistent. And at the end, we have a very small subset of finite series in these infinite families. Good. Let me explain some boring but some important concepts of this study. So let me first explain the tensor moduli space and BPS strings. So tensor moduli space is a t-dimensional coset space of this structure, which is parameterized by the collection of the scalars in the tensor multiplet. And then the unitarity on the tensor moduli space imposes the following three constraints, three inequalities. And first inequality is from the metric positivity. And second inequality is to guarantee gauge coupling scale is non-negative. And for this third inequality, we can use consistency of the shifted theory compactification on the K3 while preserving spot symmetries. But you can find more argument for this third inequality. And on the tensor moduli space, we have a very famous BPS strings, and they are BPS charges, half BPS charge sources for the two-form tensor field. Then the unitarity of these strings requires the tension of BPS strings must be non-negative as usual. Okay, and from the effective field theory, you can compute the tension of BPS string, and it's proportional to J dot Q. Q is the charge of the BPS string. So J dot Q must be non-negative. So we have these positivity conditions on these scalars in the tensor multiplet. Okay. Absolute value on where? No, J dot Q without absolute value. So J is real value. J is real.
Wow.
Bound for what?
BPS.
Yeah. Yeah. It should be non-negative. Yeah, so negative charge is anti-BPS. Here I'm talking about BPS. Half BPS. So you first choose some particular supercharge, and with respect to this supercharge, I'm imposing positive tension positivity condition. You can also consider the other supercharge and anti. Yeah. Yeah. Yeah, but it depends. So these are half BPS object. So if once you choose some particular supercharge, you are choosing particular direction, positive, for example. So this is from essentially the BPS conditions. Yes, yes. Yeah. That's, how can I? Okay. And one more condition is that these string charges must be sitting inside the unimodular charge lattice as discussed by Cyborg and Taylor. Okay, so these BPS charges form a cone called BPS cone, which is spanned by generators, which we will call CI, call it CI. So this means every BPS charge in the cone can be written as a non-negative integral sum of these generators. And furthermore, from this J square being positive condition, you can deduce that J must be also sitting inside BPS cone. So we can write this J also as the positive sum of these generators. A crucial feature of these generators, they are all shrinkable, which means they provide tensionless strings at the boundary, either at finite distance or infinite distance, depending on the self-intersection of the associated tensor multiplets. So if the C square, charge scale for the generator is negative, then it provides a tensionless string at finite distance, which is associated to the SCFT embedded inside the supergravity. And if C square is 0, then it provides the tensionless string at infinite distance in the tensor moduli space. So this is the property, crucial property for the generators. Since they are shrinkable, actually they are all classified in these papers about the 5D and 6D, 6D SCFTs and little string theories. Okay, so these generators are also generators of the CFT or little string theory embedded inside the supergravity. So for example, if C square is negative, it shrinks at finite distance. So it means at finite distance, we have tensionless string corresponding to SCFT. So this generator must be component of an SCFT embedded inside the supergravity. On the other hand, if C square is 0, then it shrinks at infinite distance. So it means it's associated to the little string or critical string inside supergravity. Okay. From the classification, you can read up all the properties of the generators like this. So this is the list of the generators we can consider in the supergravity. So we know almost everything about these generators. And from this table, you can extract a non-trivial structure of the tensor moduli space and BPS cone in 6D supergravity. So among BPS strings, there is a distinguished class of strings, which we will call H string. And this string will play a very crucial role in our discussion about the finiteness. And these H strings satisfy the following conditions. So let's call the charge for the H string as F. Then F square is 0, and B0.F equal to 2. Then F square equals 0 means it provides tensionless string at infinite distance. And combining these two together, you can compute the central charge of these strings. And then left-moving central charge is 20, and right-moving central charge is 6. And from this information, you can actually identify what is this string. And this string turns out to be actually the either critical string or little string sharing the same charge class F, satisfying this condition. So that's why I will call this string as H string, because it's related to heterotic string. In Hee-Cheol or in geometry, this H string corresponds to the D3 branes wrapping rational fiber curve on the base. So for example, we can consider base as a Hertzberg surface Fn with 1-point blow-up. Then it can be drawn in this way. Here we have a rational fiber curve with the self-intersection 0. And then the D3 brane, so this is a smooth rational fiber. So D3 brane can wrap this cycle. Then at low energy, in the tensionless limit, it provides the critical heterotic string. On this side, we have another rational fiber curve, but this time it's formed by two intersecting -1 curves. Okay, so it's a singular rational fiber curve. Then these three brane wrapping this curve provide little string. They are both H string sharing the same rational fiber curve class. They both become tensionless when the volume of this fiber becomes 0. Okay. Then from this H string and from its consistency, actually we can extract many constraints on the bulk Shikti theory. For example, the unitarity of the word CFT on H string actually requires the following. So suppose we have some gauge algebra that intersect H string. It means it induces current algebra on the world volume CFT. Such gauge algebra, I'll call it as external gauge algebra. Then unitarity of world CFT, as I explained for the question by Nopado, actually imposes the total rank of such gauge algebra is bounded by 20. Okay, this is from the unitarity. So we have constraint for the gauge algebra that intersect H string. Now I'll prove a very crucial step. So I'll prove the existence of H string in any Shikti 1-0 supergravity theory. Okay. For this, I will consider a projection of the tensor moduli space and BPS cone to the subspace, which is orthogonal to all generators with self-intersection -1. So I will call this self-intersection -1 generator as a -1 generator. And this is called blow down. And I'll define this projection in this way. I borrowed this word blow down from geometry, but this is just a projection. So you can define this projection at the level of effective field theory, okay? So after this projection, in the subspace, we don't have any -1 generators. And now remember that there is a positivity condition. J dot B0 must be non-negative. And also J must be sitting inside the BPS cone, meaning that it can be written as a non-negative sum of the generators. And these two conditions must be satisfied everywhere in the tensor moduli space, even after projection. Okay, even in the subspace after projection. Then from the classification of generators, I have shown about the list of the generators. And after projection, you can find that generators intersect B0 in this way. Okay, but here you can see only H string intersect positively with B0 after projection. So if you combine this condition, this positivity condition, together with this classification data about the generators, you see any Schick-D supergravity theory must contain H string in its BPS spectrum. So this is proof for the existence of H string. But there are two exceptions. First exception is when t equals 0 case. In this case, we don't have tensor moduli space, so our argument doesn't apply. And second assumption is when B0 equal identically 0. In this case, this positivity condition is trivially satisfied. But this case can happen only when t equals 9 case. So except these two cases, I proved the existence of H string. Okay. In geometry, these two cases correspond to, for example, when t equals 0, it corresponds to base P2. And when B0 equals 0 in geometry, it corresponds to the elliptic vibration over the base any gas surface. Indeed, in geometry, it's already known. Except these two base surfaces, scalar surfaces, all other bases of the elliptic vibration contains the rational fiber curve corresponding to the H string. So our proof precisely agrees with the geometrically known fact. The last ingredient we'll use is the containment relation between H string and SCFTs. So we claim that BPS strings with charge Q, which is orthogonal to the H string, must be element in a little string theory associated to the charge class F. So we have this containment relation. So we have a little string theory corresponding to H string. So we have any Schick-D supergravity theory must have such H string, except two cases. And if there is some BPS charge, which is orthogonal to H string charge, then it must be inside a little string theory for this H string charge class. So we have this containment relation. Even though I'll skip the detailed proof, but this containment relation can be proven by using the fact that the ratio of the tensions of the strings with charge Q and H string is always finite everywhere in the tensor moduli space. Together with the classification of SCFT, you can prove this containment relation. So let me summarize key properties I'll use to show the finiteness. So firstly, as I have proven, the H string must be in the charge spectrum in any Schick-D supergravity theories. Secondly, any external gauge algebra must satisfy this constraint. Rank of external gauge algebra is bounded by 20. Here, external gauge algebra means the associated charge Q intersect H string. And lastly, we have a containment relation. If charge Q is orthogonal to H string, then the charge Q and associated BPS string and CFT must be component of the little string theory for this H string. And these results can be proven purely from field theory argument. Okay, but geometrically, actually, I found that geometrically all these are trivial. Already it's proven in geometry. But here we prove that this one using only field theory argument. But we need two more ingredients. First one is gravitational anomaly cancellation condition. And lastly, we will use the classifications of SCFTs and little string theories. But quite surprisingly, in geometry, mathematicians don't know how to justify this gravitational anomaly cancellation condition. Okay, so this is main challenges for them to understand. On the other hand, in physics, this condition is kind of trivial. but very hard to prove these three things. Anyway, using these properties, now I will show you the finiteness structure of the supergravity series. So firstly, we can prove the tensors and their intersections in any arbitrary shifted low energy theory, which are specified by this intersection form and the charge vectors, are always realized by the topology of P2 or Hee-Cheol surface or their blobs, which are essentially allowed basis of the elliptic vibration. So this is quite surprising because this simply means tensor structure of any effective field theory can be geometrically realizable. Okay? So this means string Lamport principle holds at least on the subsector of shifted supergravity theory. What is subsector? It's a tensor sector. Okay, for the tensor sector, string Lamport principle is achieved. Even though we don't know if the full supergravity theory can be geometrically realizable, but the tensor structure can be always geometrically realizable. We can prove this using the property of effective field theory. Firstly, using the fact that H string eventually become a generator after blowdown, and BPS cone around the charge F is locally polyhedral. But I'll skip the detailed proof. But this is proven, okay? And now I will show you how to prove the finiteness of the number of tensors. For this, I use the gravitational anomaly cancellation condition. So remember that sum of the gravitational anomaly contribution from every component in the supergravity theory must be 273. So this is a very strict condition. And also please remember that only vector multiplet has a negative contribution. On the other hand, the hyper and tensors provide positive contribution to the gravitational anomaly. And there is a very interesting observation in this paper by Hamada and Lagis. They found that the only components in the supergravity theory that have negative contribution to gravitational anomaly are these S-shaped atoms with self-intersection -5, 6, 7, 8, and 12. And all these atoms support exceptional gauge algebras. And except these atoms, all the other components embedded inside the supergravity theory have positive contribution to the gravitational anomaly. Okay? You can understand this one from the gauge anomaly cancellation condition. So as I explained, only vector multiplet have a negative contribution to the gravitational anomaly, which means, so to have a negative contribution, we need to have more vectors than hyper. Then it means Q square, charge Q square, supporting the gauge algebra, becomes smaller and smaller. And eventually, it turns out that only these S-shaped atoms have a negative contribution to gravitational anomaly. And this also implies if we want to have an arbitrarily large number of tensors, because the number of tensors provide positive contribution to the gravitational anomaly. So in order to have arbitrarily large number of tensors, we must have arbitrarily large number of these S-shaped atoms. But now I will show you the number of these S-shaped atoms is actually finite. So number of tensor is finite. Okay, this is the logic. These atoms fall into the following two categories. Firstly, it can either intersect H string or orthogonal to H string. I proved that there must be H string, except very two cases with finite number of tensor. And all the string charges must satisfy either this condition or this condition. Okay, so this is a kind of trivial one. So in the first case, as I explained, they are external gauge algebras. So rank of these gauge algebra is bounded by 20. It means the atoms, these atoms, negatively contributing atoms, their number is finite because of this rank bound. In the second case, as I explained, there is a containment relation. Such charge Q and associated string must be component of the little string theory. Now we can open the classification table for the little string theory in many papers and extract non-trivial structure of these charges. Okay. Then quite surprisingly, the classification of little string theory tells us that these atoms, whenever we try to embed these atoms inside the little string theory, they do not come alone, but they always they are always accompanied by additional methods. And if we take into account the gravitational anomaly contribution from these additional methods, it turns out the total gravitational anomaly contribution from that component eventually become positive. Okay? So to see this, let me very briefly introduce the classification of SCFTs and little string theory. Maybe for this audience, I don't need to explain this, but I'll just remind you how the strict SCFTs and little string theories look like. So they are essentially generalized quivers. So now I have the word quiver, okay? So yeah, they have this following tensor base structure. So it has essentially the tree-shaped base. So basically means the intersection structure of the tensor multiplet. And this base consists of two distinguished components. One is node, the other one is link. And what is node? Nodes are these white circles. And node is nothing but the single tensor multiplet with the self-intersection minus 4, 6, 7, and 12, up to 12. And link, what is link? Link is a finite chain of tensors with the self-intersection minus 1, 2, 3, and 5. But here, important thing is that whenever you have node, and if we want to increase the number of node, then you should increase number of link. Okay? So if you look at these atoms, then these atoms with the self-intersection minus 6 or less, they are all nodes. So if we want to increase the number of these atoms in node, then you should connect this node with the link. Okay? So you cannot just put these atoms individually. They always comes with additional tensor and method contents. In particular, interior links are nothing but the conformal methods discovered by Michele. He left. Where is Alexandro? He also left, maybe. Yeah. Anyway, we don't have authors. Anyway, they discovered this object in 6 dimensions. Conformal methods, yeah, again, I think I don't need to explain, but roughly, so every internal link is a conformal method, and they connect node. Nodes are essentially the these negatively contributing atoms. We want, say, the number is finite. Okay. So node and link, they come together, and if we compute their gravitational anomaly contribution together, then roughly their gravitational anomaly contribution is bigger than or equal to 30. So for example, if we want to have more node with the self-intersection minus 12 supporting E8 gauge algebra, then they must come with additional conformal method, for example, E8 times E8 conformal method. Then this total contribution is exactly, the gravitational anomaly contribution is exactly 30. And similarly, you can compute this combination for any possibilities from the classification table. Then you can show their gravitational anomaly contribution is roughly bigger than or equal to 30. Actually, bigger than or equal to 30, except one example. One example has a gravitational anomaly contribution 28. Okay? This means in this second case, we have positive contribution to the gravitational anomaly. So because of this gravitational anomaly cancellation condition, we cannot have arbitrarily large number of these atoms. So this proves number of tensor multiplet in strict supergravity is finite. Okay, so T is finite. And here I didn't explain, but this is a bottom-up argument. And actually it covers all the cases, including the frozen phases and Yuan gauge algebras. So this is a generic argument for the finiteness of number of tensors. And once we prove the finiteness of number of tensors, you can easily argue number of vector and hypers are both finite. And together, this establishes the finiteness of the number of massless fields in 6 dimensions. Okay, we can go further and actually compute the exact bound on the number of tensors and rank of gauge algebras. And idea is very straightforward. We first identify, using the classification table for the little string theory, the composition of the atoms for the H string such that it can host large number of tensors. So because we want to build a large theory saturating the bound. and the highest rank of gauge algebras. And for the given H-string configuration, you attach external tensor multiplet and gauge algebras. Okay, so we have several little string theories for the H-string, and we attach external tensor multiplets and eventually form a supergravity so that the resulting theory contains the maximum number of tensors and highest rank of gauge algebras. So this is our idea and our scheme, but the details is very technical, so I'll skip the details and explain the final result. So we found the theory having maximum number of tensor is given by this tensor-based structure. Okay, so here E8 cross E8 is E8 conformal method, and this supergravity theory contains a single little string theory for the H string consisting of 16 E8 times E8 conformal method, and it's attached to two external E8 atoms with the self-intersection minus 12. So this one is external atom, and this one is another external atom. In total, it contains 193 tensor multiplets and this big gauge algebra. So this is the maximum tensor theory we can construct in 6 dimensions while preserving all the required conditions, such as anomaly cancellation condition, okay, and existence of H string and so on. So number of tensor is bounded by 193. And this is another maximum theory, but this time it's the maximum rank theory. Again, this time we have a single little string theory with this affine E8 type tensor base supporting SO and SP type gauge algebras. And this little string theory intersects a single SO32 external gauge algebra. So this is the external gauge algebra. So if you remove this one, it's just a little string theory. But one more tensor make this theory as a supergravity theory. And this theory contains 9 tensor multiplets, and rank of gauge algebra is 480. So in 60, we have bound. Number of tensor is bounded by 193, and rank is bounded by 480. And this is sharp bound. I will explain. It turns out that these two theories are realized in string theory. They are theories living on the 24 instantons in E8 times E8 and SO32 heterotic strings compactified on K3 with the E8 singularity. And these theories are actually investigated very early in these papers. Okay, so this fact that the theories saturating the bound we found are realized in string theory provide very, very strong evidence for the string Lampos principle. And lastly, sorry, how many gauge groups? The second one or first one? So these gauge groups. It's very big theory. But rank of gauge algebra for this gauge group is just smaller than this one. Exactly. So as you know, so it's E8 cross E8 is E8 conformal method, and E8 conformal method has these gauge algebras connected by E8 gauge algebra. Okay, so in total, this theory contains this big gauge algebra. Okay, so you can try to add more tensors or more methods. Okay, for example, you can try to add more tensors. Then whenever you add a tensor, it increases gravitation anomaly, and gravitation anomaly cancellation condition would be violated. So this one is precisely the theory at almost the boundary of the gravitation anomaly cancellation condition. Okay. Metric on the tensor moduli space.
Do you have any effect on the form of the space, compactness or something?
No. So metric is just flat. So here I'm talking about the flat Minkowski space.
Yeah, but
Yeah, it's flat. Yeah. On the flat background, I'll just consider small fluctuation. Any other question?
volume of each string
If
bound.
oh, so you are talking about if there is any implication from the word safety on this bound. Actually, here I secretly use all the constraints coming from the consistency of the word safety living on H string already. So it's complicated encoded in here. But in particular, as I explained, H string must exist. And actually, we imposed that H string support as many as tensors. Yes, yes, yeah. So this configuration preserve a unitarity bound for the as in this case. So for example, only unitarity bound is imposed on the rank of gauge algebra for the external tensors. It's EA times EA. It means the unitary bound is preserved because rank 16 is smaller than rank 20. So it's not at exact bound, but anyway, it's satisfied. Yeah.
Didn't from the rank max theory because
Rank max theory, okay.
was not the case, one of the two cases where the H string is not that right. So
Sorry?
there is one of the two exceptions in which there is no H string, right?
This one has H string. Oh, okay, good, good. So you're asking, so I have explained that the proof about the existence of H string is violated for two cases. One is T equal 0, the other one is T equal 9. You're asking about T equal 9. But actually, T equal 9 case, not only that condition, but we need the condition that B0 equal identically 0.
Oh.
Yeah. If you have such condition, we cannot impose any constraint coming from H string. But this one, B0 is not identically 0.
Okay, so
Yeah.
it's an H string.
Yes, yes. Yeah. Geometrically, it's roughly, so it's associated to the complex structure moduli deformation of the DP9. Yeah.
Possible to saturate both boundaries? Is it possible to saturate both?
No, there is no such issue. Yeah. Good. Any other question?
The other one is made of silicon bond. And
Yeah.
what is the other I can make a maximum of that tensor? Then rank and then the
Sorry, your question is we have the constraint coming from the gauge anomaly cancellation condition. We have many constraints, and we imposed all such constraints here. But what is it?
So silicon bond you maximize the tensor, you make it rank.
Sorry.
Can you maximize number of hyper?
So maximum number of hyper. I didn't compute the maximum number of hyper, but once you have this bound, you can easily compute the allowed maximum number. I don't know if it's realizable by using the gravitational anomaly cancellation condition. So here you can just put maximum number of vectors and tensors so that you can maximize the number of hypers. Yeah, yeah. But I didn't compute the sharp bound on the number of hyper. Yeah. Because usually we don't ask that question in geometry. Yeah. So good question. Yeah. So this is a sharp bound. And it turns out that they are all realizable in geometry. Okay. So maximum tensor turns out to be associated to an elliptic Calabi-Yau threefold with over the base given by 192 block of algebra surface F12. And this total Calabi-Yau has these such numbers, and base have this such number. And maximum rank theory is associated to another elliptic threefold over the base given by a point block of algebra surface F4, and it has these such numbers. And furthermore, it turns out that these two theories are T-dual to each other on the circle compactification. And you can see total, so Hatch numbers of total space of these two geometries precisely agree. Okay, they are T-dual to each other. And this resulted that these maximum theories are realized in geometry predict sharp bound on the Hatch numbers of elliptic threefold. So we claim now the Hutch number H1 of total Calabi-Yau is bounded by 491. And Hutch number for the base of elliptic vibration is bounded by 194. And the H2 bound was already studied by Taylor in early 2012. And these two maximal series are sitting here, very corner in the Calabi-Yau database. Okay, so we have a here isolated point, and these two geometries correspond to this point. And we are predicting now that there would be no more elliptic threefold along this direction. Okay. Okay, let me conclude. So I have shown that in Shakti 1-0 supergravity, number of tensor and rank of gauge algebra are bounded. And here I used the consistency of the moduli space physics and unitarity of VPS string. And in particular, we used the classification data of the Shakti SCFTs and little string series. So this data provide very, very strong constraint on the gravitational series. And we found this bound. And yeah, we can consider the following problems. For example, we made a prediction about the H11 on the elliptic threefold. So it would be interesting if we can actually prove geometrically this bound. So actually, Seungju and Kosha, they made some bound on the number of tensors. It was 567, but they need more data to find this bound. And I talked about mostly the perturbative anomaly cancellation condition, but probably we can extract more constraint from the discrete symmetries. Okay. So actually, Hamada and Lajes, they used the Difreed anomaly cancellation for the two-point gauge field to have their bound, but maybe we can extract more information from the discrete symmetries. And we discovered the new structure of Shakti supergravity series. So it can provide new classification scheme for Shakti supergravities. So now I think we can classify all allowed Shakti supergravity series in systematic manner. Okay. Okay, let me stop here. Thank you very much.
So is it correct to say that you have reduced in this context the gravity lamppost, string lamppost conjecture to SCFT lamppost conjecture?
No, I can. So they are quite different in the context.
Yes, in a sense, you rely on classification of SCFTs, which comes from the assumption that they are all realized.
Yeah. But yeah, this classification involved all the realization method. So this is a reasonable assumption, I think. But the lamppost principle for the SCFT is a bit, yeah. But I think in this audience, most people believe the classification, right? Yeah.
What he says is that you assume that we know all of them.
Yeah, I'm assuming. Yeah, I'm assuming. Yeah. So you're asking if some of them are not actually realizable. Yeah. I think we believe, right? Yeah, okay. Yeah. A good question anyway. But the more problematic one is whether we can find new component other than the component we know in the classification. Then maybe it can actually kill our program. Yeah. So it's a still open problem. But as you know, any proof always comes with assumption. So yeah, we made some assumption. Yeah.
Some kind of maybe studying 5D in book 1.
Very good question. In 5D, we can try. Actually, I have tried. But problem is in 5D, we don't have anomaly cancellation condition. But anomaly cancellation condition was crucial to anyway cut down huge number of possibilities. It was very crucial in this program. But in 5D, no, I don't have. Yeah.
Allow only 25.
Sure. Yeah. It's very good program, but Yeah, I have no idea how to bound the 5D series. Yeah, for example, if we can prove the number of Calabi-Yau manifold is finite, yeah, it's great. Yeah, but even by assuming the realization in geometry, I cannot actually attack this problem in 5 dimensions. 성재, 그렇지.
Sorry for question from me. I mean, the decoupled gravity we can add as much as
Yes.
another
Yes.
tensor. And for
Yeah.
example, we consider multiple and fibrane,
Yeah.
then we have tensor. But does it mean that if we do not decouple gravity, we cannot coincide the fibrane?
No. Here I'm talking about the full supergravity theory. But M5 brains, for example, we can consider. So M5 brains are living in 10 dimensions as a defect. Okay, so when you talk about the theory living on M5 brains coupled to the gravity, you have to think about the gravitational theory in 10 dimensions. Okay, not in 60. Okay, so I'm not talking about any bound on the number of some defect object in 6 dimensions. Okay, there is no such bound. Yeah. No constraint at this moment, but maybe you can find another constraint. Yeah. I don't know.
Do you have an example of a little string theory?
Yeah. What is your question? We know there are little string theories. Yeah. So for example, if you cut this two external tensor node, then it's a little string theory. Yes. Yeah, cut means if you take the large volume limit for this minus 12 tensor multiplet, then you get the little string theory, isolated in 6 dimensions. Yeah. So it's a limit in the supergravity theory that reduced to the little string theory. Since I have proven the existence of H string, we always have such a little string theory, except 2 cases. Yeah. Thank you.